before, the decision tree is one of the easiest machine learning models to understand and amazingly powerful for something so simple. The decision tree just has a series of if statements. If one parameter is greater than something, put it in one category and just make a series of if statements, so it's very easy to understand how it works. But alone, a decision tree is not very powerful. What makes it powerful is to make a forest, which is a whole bunch of decision trees, and you combine the outputs to get a better output by averaging out the error. And you can even make random decision trees that have random locations of the threshold, and random choice of the parameters, where they just sort the data into arbitrary subgroups, and you can still combine the output and be quite powerful. So here you make a data set with two moons again, so there's blue dots and green dots, and there is a distinction between them, but it's not as simple as just being x1 greater than a threshold or x2 greater than a threshold to sort them. You're going to have a more complicated boundary between them to do a good job of sorting them. And so you can make an ensemble. Now, an ensemble just means you make several different types of machine learning models and combine them together. So you have a support vector machine, a random forest, and a logistic regression one that models the output as a raw signal input. You can make those three things, and then you can see how accurate they are. And here you are. The logistic regression alone gives you, let me just zoom in on this in a way that's there. The logistic regression alone is 86% right. The random forest is 89% right, and the support vector machine is 89% right, but when you combine them all, you get up to 91% right, which is the point. If you have independent measurements, and the noise will tend to cancel out, and you'll be more accurate by combining them. Now, this was done by just choosing 2 out of 3. If 2 of them agree and the third one is different, then you take 2 out of 3. That's called hard voting, and it's a very inefficient way to combine measurements because, in fact, their measurement is has more information than just saying which one I prefer. They have like a probability. And so you could have soft voting, which instead of you take the probability and you average the probabilities. So if one of them is 60% confident, another one is 90% confident, in hard voting you would just treat them both as the same, but now you take the one that's more confident and treat it as more significant, which you should. So in that case, you go from 91% up to 92% combining them. So, all right. Now you can try bagging to make a forest. And what you do is you make many random subsamples of the training set to train them on. So you pick a certain number of items for the bags, and here we have 500 estimators. That's 500 decision trees we're going to make. And we're going to take samples of just 100. So we're going to make forest with 500 trees, and we're going to pick a random 100 of the training elements for each one. So they get trained on different data, and therefore they'll come out different, hopefully independently different, and then you combine them together. And so the result is a single decision tree, really badly overfits the data here. This is overfitting. You can see you're putting some region of orange up here where it doesn't belong, some region of green here where it doesn't belong. This is not following the real trend of the data. This is fitting the random variation of the data. But this is what you do with bagging, where you combine many decision trees. Now you really get close to what looks like the optimal solution, where you really draw this curved boundary to follow the shape. And remember, this is all done with just this chain of if-then statements. So it's easy to understand and fast to run. And so there are some flags to find here. If you work with only 5 trees, then it's much simpler, but you can still have an overfitting here and over here. But without bagging, you get this, where you train all 5 on all the data, and until they all just conform to the noise. Here you use bagging, so they're trained on different subsets, so they much more closely follow the trend of the data and not the noise in the data, which is, of course, what you want. And then we can talk about other things. AdaBoost is adaptive boosting, and this is where predictors are trained sequentially. Instead of just having 100 random trees, you have a predictor that does some approximation to the data, and then you make another predictor to correct the errors of the first one. So here, you're trying to fit this curve, and as you can see, you did pretty well here, but then you're too high over here. And so the next one, you have a correction term to try to fix the error in the first one to get a better fit. And so each one trains on the residual error from the previous one, like successive approximation. And they call that AdaBoost. And you can run that one and see how well it works. And you'll see if the learning rate is too high, which means it makes big jumps to try to move, then what happens is it starts here. This is the first one. And the second one is over here, which looks pretty good, but the third one is way over here, and the fourth one's way over there. And this is what happens in iterative training if your step is too large. The minimum is here, you jump past the minimum, then you overshoot it again, and you diverge instead of converging to a good minimum. This is what happens when you try to learn too fast, because when you learn, you assume linearity. You do a partial derivative on all the parameters and figure out what direction will lower the error, but that assumes it's linear, and if your step is too large, it's no longer linear. So your predicted new value parameters is not actually getting closer to the bottom. So you have to lower the learning rate. Like here it is a learning rate of 0.5, and now you can see it converges to, again, a good solution, a nice curvy decision boundary between those two, like it should be. And then you can do it again with 10 cycles. You can see with one, it just goes all over the place, but with a much lower learning rate, it nicely converges to a good logical, clear separation. So that's the joy of random forests. And they're considered actually one of the most powerful models available today for classifying.